Cool guys, so today we'll be discussing lazy segment trees. And before we get started, like basics of segment trees should be clear. Only then this particular session would be helpful for you. Cool. So let's draw a very basic segment tree. Like this is the very basic segment tree, or you can say it's just a binary tree. The only difference is that in case of a segment tree, you would have ranges being stored on nodes rather than just values, right? So I've drawn this skewed. It's not totally skewed, but yeah, it's not a complete binary tree over here. Let's say the leaf contains the value a1, a2, a3, a4, a5, a6. I'm just doing that all of this so as to jog up your memory. If you feel there's any doubt, just let me know. And this would contain a1 to a2. This contains a3 to a4. This would contain a5 to a6. And yeah, this is also a leaf node. Let's say this contains a7, right? This would be a5 to a7, this would be a1 to a4, and this would be a1 to a7. And doubts in this? Or all good? Yeah, the recording is on. Cool. So now what we learned in the previous lecture is that we can have different type of segmentaries, or the one of the most basic one is that the segmentary would help you with two operations. One is range queries, right? And the second is point updates. We also went for the code for the same, and we also looked at a problem from CSCS. We saw how range queries are happening, and in both of these cases, the complexity was order of log n, where n is the number of leaf nodes, you can say, or you can also say number of nodes, because both of them are essentially the same. But as a end user treating this segment tree as a black box, you would be only interested in the leaf nodes. So let's stick to that. Cool. So now, what's the benefit of having a lazy segment tree? The only demerit you see over here is that you can have range queries. So you can say that, okay, I want the sum or the XOR maximum or minimum for the of the range L comma R. So we can just say that, okay, give me the operation, like give me a value that applies on the range L to R, right? That's pretty good, and you are able to do it in order of log n, right? Irrespective of what your L and R is. It could be the entire tree, or it could be a part of it. It could be as small as a single node itself. But yeah, irrespective of the values of L and R, the time complexity you are getting is order of log n. The problem is it's only limited to point updates. So I can only say that, okay, go and update the value of the node, maybe like uh, k, to some new value, right? Or maybe update its value, add something over here, or whatever. So now the problem is, if I say that, okay, go and update all the nodes in the range L to R, then essentially what you'll have to do is you'll have to firstly go and update one node, right? Then you'll update the other, then you update the rest. So let's say I want you to update the nodes in the range L to R. So what you'll essentially do is firstly you'll update L, then you'll update L plus 1, then you'll update L plus 2, so on till R, right? And in the worst case, I could ask you that, okay, go and update all the nodes from 1 to n, right? In that case, the complexity would be, for the single operation, the complexity is order of log n. So in entirety, the complexity would become order of n log n, right? This is something we didn't want. We wanted our complexity to stick to order of log n, right? So how do we deal with it? The solution is lazy segment tree. Now, how does lazy segment tree even help? Lazy segment tree is a way of telling your segment tree that I want you to make some updates, right? But again, I'm not really sure if these updates are even beneficial to you at this point in time. Like you can store some information in your data structure. So whenever I'm doing this kind of talks, I'm basically like trying to convey information to my data structure, right? And I'm trying to hear back things it's saying to me. So what I'm gonna say to the segment tree is that, okay, I want you to update a particular range, but I don't really want immediate results from you. So what do I mean by that? So let's say I ask my data structure that, okay, I want you to update all the values from a1 to a3, right? So I'll say that, okay, take this information from me, but again, I'm not looking at the data structure as a whole, right? So the thing is that you take the values, And whenever I ask you another operation, right? So the thing should be that they should be consistent. Now, what do I mean by that? So let's say my array initially was 1, 2, 4, maybe like 5, and then 8, right? And then I said that, okay, update all the values from the range. And we are saying zero base index, one base indexing, so 1, 2, 3, 4, 5. So now I say update all the values in the from index 1 to 3, make them 5, right? So essentially, the array should be 5, 5, 5, and then 4, 5, 8, right? However, when I'm giving this update operation to my tree, to my segment, to my lazy segment tree, right? I'll say that, okay, this is the kind of operation you want to do, but the internal implementation is totally up to you. I'm not even going to check whether you have updated the values in real or not. But in future, whenever I'm going to ask you for some values, so maybe I'll ask it that, okay, return the maximum in the range 1 to 2, right? From the indexes in the range 1 to 2. So you should then return me 5. It shouldn't be the case then that at that time you return me 2 or you return me 1, right? So whatever operations I'm going to perform should be consistent. Rest, the entire implementation is up to you. Till this point, any doubts?
Nope.
Okay, cool enough. So now what our lazy segment trees does is it becomes lazy, right? As the name suggests. So it says that, okay, till the time I'm not forced to make some updates, I won't do it. Now, how would it do that? Let's try to imitate this particular scenario right over here. So let's say this is a segment tree, and the values we were having is 1, 2, 4, 5, 8. So there are a total of 5 values. Okay, let's draw this. Okay, so this is a 1, 2, 4, this is 5, this is 8. How that works, right? Now I ask my segment tree to update the values. Okay, so these are the indexes. This is 1, 2, 3, 4, 5, right? So the first operation I'm going to do is update all values from 1 to 3. When I'm writing this, I basically mean the indices to a value 5, right? So what it'll do is it'll come to the node, root node, and then it will say that, okay, what's the range I contain? So it will say that, okay, you contain the range 1 to 5, right? So it's having uh, it's a parent of the nodes in the range 1 to 5. And what do you want me to do? I want you to update the range, update all the elements in the range 1 to 3. So yeah, it will do the very same stuff that was of calculating the mid, etc. Now, if you have taken one base indexing, the previous examples were of one base zero base indexing, so there would be some changes. But anyway, not getting into the integrities, it would actually move to its left because this contains the range 1 to 3, right? Now it's gonna tell to this particular node that, okay, I have a operation for you, and the operation is that you need to make all your children 5, right? Irrespective of what their value is. So it'll store some information in itself. So this particular node itself would store some information, and the information basically would be that, okay, update all my children to 5, right? And what it'll do is, for example, over here, I was talking of a max operation, right? I was talking of a max operation. As soon as this value gets the information that I need to update all my children with the value 5, what it's going to say is that, okay, I'm going to store this information inside of me so that I can relay this information to my children. But for me, let's update the values. So right now it would be having the max as 4, right? The max value over for this node would be 4 because one of its children right over here is having a value 4, right? So it's going to say that, okay, now I need to update all the children with a value to a value 5, right? And 5 is greater than 4. So obviously my value is also going to change, right? So I'm going to say that, okay, my value is going to become a 5, right? And also over here, I'm storing this information that I need to I need to relay this information to my children that all of your values have to become 5. Any doubts? This is the very crux of it. Like the only difference between a segment tree and a lazy segment tree is this one. So if you have a doubt, please let me know. Let's work on this before we proceed further. Hey guys, any doubts? Okay, understood. When I read no means you have a doubt. Okay, that's cool enough. Let's wait for one other comment. And nope, good enough. Cool. So another point is like over here, I was just saying that okay, we'll store the information like update all my children, but technically the data structures don't work that way, right? It can't be the case that you're gonna write a string over there and then it's gonna interpret what you meant and relay the information further. So what are we gonna do over here? Thing is, since it was a operation as simple as updating the values, I can just store this information inside of an array, right? And if you remember from the last lecture, all of these nodes, right? All of these nodes were present inside a tree array, right? That was of size 4 into n. And that's why I'm saying that the previous lecture was important because we are going to build on top of it, right? So we already had an array which denoted what's the sum or the max or the min of its children, right? And similarly, we can have another array now. This is tree, and now we'll have another array that is lazy, right? Now, what lazy would contain is okay. Now, lazy would contain the information of what do I need to tell my children. For example, let's say this is the node 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, and so on and so forth. Let me just read all this because this probably would become important. Let's try to number the nodes as well with a different color so that it doesn't become confusing. Okay, let's make this color. Cool enough. This is node 1. Let's increase the size. This is node 2, right? This is node 3, this is node 4, this is node 5. Okay, I updated. Okay, this is node 5, this is node 6, this is node 7, this is node 8, and this is node 9. Cool. So now inside the lazy array, I'm gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just up till 8, I guess, but never mind. Yeah, up till 9, I guess. So now what would happen over here is whenever I'm gonna update a particular value. For example, over here, I said that this particular node, right? This particular node needs all its children to have a value 5, right? So I can pass some values over here. What's the index of it? It has index 2. So at 2, I can say that okay, give it a value 5, right? So and this for the tree itself, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And over here also the values would get updated. So the maximum over here would point to 5, and this information suggests that all of its children should also have a value 5. Now why does this become important? We'll come back to that. So now let's say our operation was give me the maximum in the range 1 to 2, right? In the range 1 to 2, that's the next question I'm going to ask my system. So give me max in range 1 to 2, right? Now what it's going to do is again it's going to start over here, right? It's going to start over here. It's going to say should I move to my left or my right? It's going to move to its left, right? Again it's going to say should I move to my left or my right? It's going to say again left. However, now it will observe that okay, my lazy doesn't just have a value 0, right? It has stored some value that is 5. So what does this mean? This essentially means that I'm having some value which I need to propagate to my children. So let's do that. But hey, right now I can propagate to the left child because I want to go over that. But what about my right child? So I'll say that okay, this is just one step, right? This is just one step. Let's also do that. You are going to propagate to your the value to your left child. Let's propagate it to your right child as well. That's not a big problem for me because like asymptotically it's not going to add much to your time complexity, so that's fine by me. So its left child is the node. Okay, so this had to be 3. Okay, give me a second. Yeah, I mistakenly wrote this at the wrong place. This had to be over here. That had to be over here. This had to be okay, over here. Fair. Now for the node 2, right? Its left child is 4 and its right child is 5. So it's gonna say that, okay, let me propagate this value to my children. So 2 would say, like this value would now become 0, and this value would be propagated to its children. So now both its left and its right children would be having a value 5. Also, like we did for this particular node, as soon as your lazy is getting updated, you also need to update the values in your tree, right? So the same procedure that this particular node had followed, would be followed by its children as well. That they'll see that, okay, I'm getting a new update for me. That basically means all my children need to have a value 5. So should I update my maximum value or should I keep the same? That's what they are going to do, right? So once we are done with that, this node would also be having a value. Okay, let's decrease the size. Okay, this node would be having a value max equal to 5, right? And that's what it's going to return. Cool enough. Any doubts in this? Sometimes, okay, not yet. Cool enough. Yeah, that's pretty much it. That's all about lazy segment trees. Even if I show you the implementation, you'll be amazed. Like, it's not totally different than what we had done earlier. So building some context over here, this segment tree. Okay, let me just write. Okay, let's remove this. Okay, so what this segment tree does is, it adds the values to a range, right, and then checks for the minimum value in a range. So basically it supports two kinds of operations. That the first one being that you can say that, okay, I want to add 1 in the entire range of L to R, and the second operation being that you can ask for the minimum value in a range L to R. So let's see how it's working. But like coupling it with the previous implementation of segment tree we saw, so a lot of things are same. For example, this build function, this build tree function, this is exactly same, right? The only thing is that over here I'm defining a combine function. Combine basically is a simple function like we talked in the previous lecture. It's just going to take the two values, right? Or you can say for the parent, it's going to update the result. So over here we are talking of a min segment tree. So it's going to say that this particular node of the parent is equal to the minimum of its two children. What next? We do have a query, right? Query is also same. There's one function that is different, that is push down. Don't worry about that, we'll talk about it later. But yeah, other than that, even the query operation is same. Okay, I moved it. Yeah, even the query operation is same. What's the other one? The other one is update, right? So if you look at it, even update is same, right? So technically it's the exact same implementation we saw for a simple segment tree. The only difference is this push down function, right? Now, what is this push down doing? That is something we have to see. So let's look at the push down function. So our push down function takes in three values. That is v, that is basically the index of the node, a tl, that is the tree left, and the tree right. It's calculating mid, which we are not going to using, but I'll tell you its importance. Okay. Required. Let's just write it that way. Cool enough. Then what it's doing is it's saying that the values in your left and your right child need to be updated, right? But by what it should be updated? It basically needs to be updated by whatever was stored in my lazy. Now, how does that make sense? Let's get back over here. So let's say over here in the segment tree we are like currently learning about, or the lazy segment tree we have currently coded, it's performing two operations, like just add x to all nodes, all indices in range in L to R, right? And the second is get minimum of all indices in range L to R, right? Cool enough. So now what it's doing is that if this is your segment tree, or this is a part of your segment tree, let's say, right? And I already know that the value over here, the lazy of this particular node says maybe like a figure like 10. So this technically means that all your children need to have their values increased by 10, right? So if that's the case, then when I'm gonna go down, right? If I'm gonna go down, then I can say that okay, whatever value you were storing. So let's say the like the values over here were maybe like 20 and maybe like 25. So the maximum or the minimum it was storing was actually 20, right? Now I'm just gonna add 10 to each of those nodes, right? So in the tree itself, okay, okay, that's bad. Okay, in the tree itself, the tree of this particular node was saving a value. Let's call it tree v equal to 20. Now you can say that okay, after this updation, tree v would actually contain 30, right? Because 10 is gonna get added to both the nodes. So this is gonna become 30. This is gonna become 35. So the minimum of 30 and 35 is 30. So your tree v is gonna contain 30. And how did this happen? Because we knew that the parent has a lazy value of 10, it's gonna get added to whatever values are there in your tree or in this particular node, right? So we got a 20 plus 10, that is 30. Cool. Yeah. For some, yes, it would be the same, but what you can do over here is, so this is something I was gonna teach in maybe like 5 minutes, but since you already brought it up, so cool. Let's deal with that also. So let me just teach it over here. Now, some is something I'm not gonna code it up, but it's a good doubt, so I'll explain it over here. So essentially, what's happening is that you also have the tree left and your tree right for each node, right? Now tree left comma tree right, if you simply do a tr minus tl plus 1, that would give you the number of nodes in this segment, right? Now let's say the operation was a bit different. The operation was sum and I wanted to add maybe like plus 5 to all the nodes, right? So obviously by how much value would this value increase? It would increase by whatever the existing value is. Let's say the current sum is sum plus equal to the number of nodes into whatever value you're trying to add. Over here we are trying to add 5, so let's just add a 5 over here, right? So now the new value of your sum would be the number of nodes into 5, and this is how you can calculate the number of nodes. Cool. So in brief, whatever kind of change you're gonna make, right? It could be a max, min, XOR, sum, even other things like this. You can totally update your values, or you can add things onto top of it, set it to a new value. Everything is doable as long as the operation you're performing can be performed by some mathematical operations using the tree left, the tree right, basically the range for which you are gonna update. If so, a tree left and tree right can get you the number of nodes, right? So once you have the number of nodes, doing operations wherein you have to calculate that what would be the total value that would be added becomes easy, right? And yeah, that's how it works, right? So basically we say that for my left child, just add the value whatever I'm having at my lazy. For my right child, just add the value whatever I'm having at my lazy. Also, the lazy needs to be updated, right? Because my left child could also already be having some values, but now I'm giving it some more values to add on to, right? So yeah, update those two also. And now this is important. And now I am free of my responsibilities. So this is what exactly we discussed over here. So since it has already propagated its values, right? So we don't want the values to be propagated again and again. So we have to set it to a zero, right? So we are setting this value to zero. That okay, now you're done with functions, and now you have nothing to propagate further. So go and set your value to zero. Everything has been taken care of, and your tree is again in a consistent state. So yeah, that's pretty much it about a lazy segment tree. For the snippets, I'd say this is a very standard snippet I'm already having, and I have already shared the resource for the GitHub repo. You can use it from that. But yeah, if there are any doubts, I'm more than happy to answer them. Okay, let's see. Is there any problem in add to tree v only instead of v2 in push down function? I didn't understand your point, bro. By the time, if anyone has another doubt, can you please pick up? Or did everyone understood everything? Can't we directly add to parents instead of passing it to children? Yes, so we can do that. There are two kind of implementation. The reason not to discuss the other kind of implementation is because it kind of becomes confusing. So yeah, you can do that, but then you have to completely change your implementation. That's pretty much it. Any other doubts? Yeah, you have to actually. So the thing is that it's not tough. Like lazy segmentary, the problem is good resources aren't there for lazy segmentaries. So even I had to study it from some blogs, I guess. But the overall concept is easy, right? If there's still some doubts, we can wait for 5 minutes. We can answer a few doubts if there are any, and if there aren't, anyway, I'm gonna close the recording. So yeah, that was lazy segmentary for you. I'll share the snippets and you can save those snippets further. That's exactly what I do because let's say if I'm in a contest, right? Let me show you how I do that. Let's say I'm in a contest, so I'm not gonna code this entire thing up. So I have a like snippet called sec3. So I'll do sec3 snip, and it gets auto populated, right? Then I can directly change it. And let's say even if I need to make some changes, so this is a minimum segmentary. Let's say I need a maximum segmentary. So for that, I'm gonna say instead of int max, I'm gonna make it a int min, right? And instead of max using min function, I'm gonna use the max function. Small changes everywhere. Let's say instead of updating the values, like instead of adding values to my existing value, I just want to update them completely. In that case, all of these functions would change, but the essence more or less remains the same. So understanding the very basics is the most important thing, and then practicing a lot is what would make you better at these concepts. Well, I'm closing the recording now. Any doubts? In a nutshell, we are maintaining a lazy tree array, forgetting the updates down the tree while we are fetching. Exactly. Yeah, that's pretty much it. You got it. Totally, you totally got it. So the idea is we are not gonna update the values at a lower level until and unless it's necessary. And when I say until and unless it's necessary, it basically means until the point in time you actually need the value and you are querying for it, right? So let's say I'm updating the entire tree, so only the root node needs to know about this particular information and I can keep updating it as required, right? So that gives us a better time complexity because we are not doing useless work over here. We are only doing the work that is essential, or you can say at most essential, and saving down on complexity. And over here we get a time complexity of order of log n for both the operations, that is for a query operation and for update operation as well. Closing the recording now.